Hey guys, so this is Unit 5, Video 2, okay? And it's energy conservation. This is the last video of the energy unit, all right? So here we go. So the goals for today are to describe how energy cannot be lost or gained, solve for kinetic and potential energy in simple real-life situations, and solve for the conservation of energy, all right? I want you, before we kind of start here, I want you to remember that the energy of motion is kinetic energy. We use KE, we do not use K, so cross that out, okay? Whenever an object is in motion, it has kinetic energy. All right, sorry, my pencil is out of lead. One sec. Okay, sorry about that. All right, so whenever an object is in motion, it has kinetic energy. The faster it's going, the more it has, okay? The energy due to gravity is called gravitational potential energy, or PE with a little g. We're going to specify why we have that little g there today. But this is the stored energy based on the object's height, okay, which gets higher the farther off the ground you are. So basically, the higher you get, the higher the potential energy is, okay? Now, the reason we have to specify that little g for the gravitational potential energy is because there's other types of potential energy. One type of potential energy is the spring potential energy. So this is the energy that is stored in a spring. Like if you were to compress a spring or you were to stretch it, and then you were to let it go, right, it would do something. It would either expand if you had compressed it, or if you had stretched it, it would compress back to its original length, right? And so that energy that it holds while you're stretching it is called the stored potential energy. We're going to actually call that, we're going to put PE of a spring, right, the little s, okay? And the equation is 1/2 kx squared, all right? Where K is called the spring constant, so I'll just make a little note of this over here. Okay, K is a spring constant, and it basically tells you how tight the spring is, or how strong the spring is. So the harder it is to stretch or compress, the higher that K, the higher the spring constant. If it's like a slinky and it's really easy to compress or stretch, then it's going to have a low K, or a low spring constant. Okay. X is the distance from equilibrium, so meaning that if the spring is naturally sitting like this, right, and then you were to take it and you were to stretch it out like this, right, then the distance from, let's say that originally its comfortable length is here, right, then your X is how far from that length you stretched it, okay? So this is its equilibrium length. Okay, we'll call that LE. All right, and then this is the amount you stretched it from its equilibrium point, okay? And the units for that are going to also be in joules because it's a type of energy. All right, we'll talk more about that in class. There's also stuff called chemical potential energy. This is the potential energy stored in chemical bonds. So molecules have chemical potential energy due to the bonds between the electrons. So when these bonds are broken, energy is released, which can be transferred into kinetic or potential energy. So this happens when we eat food, and then we use that stored energy to then exercise or just do our normal tasks through the day. That stored energy from the food is called the chemical potential energy, okay? All right, so the more important part of this lesson is the law of conservation of energy, all right? And what this says is that energy can be transformed from one kind to another, so it can change from potential to kinetic to spring energy. But if the total energy at the end of the process appears to be less than at the beginning, the lost energy is not really lost, it's just been transferred to another system, such as heat or sound or some other form of energy, okay? So energy, the law of conservation of energy states that in any closed system, including the universe is a closed system, the total quantity, the total amount of energy remains the same all the time. Okay, so energy is transferred from one form to another, but it will never be lost or gained. So you can't just add energy to a system without giving some up from yourself. Okay, so it cannot be lost or gained. All right, so we are talking about mechanical energy. Okay, mechanical energy is kinetic plus potential. Okay. So mechanical energy is kinetic plus potential. So our conservation of energy law says that the total mechanical energy initial equals total mechanical energy final, which means that the kinetic energy initial plus the potential energy initial equals the kinetic energy final plus the potential energy final. Okay? Sometimes you see a U here. Sometimes, like college or sometimes books will use U for potential energy. I don't know why. Okay, it's just what they do. We're going to use PE on all of our assignments and things like that. But if you see U like in your book or something, it's just because sometimes we'll use U for potential energy. Okay, but conservation of energy. This is a very simple equation. It just means that the total mechanical energy, meaning the kinetic and the potential, all the total energy before equals all the total energy after. Okay, and that's what this equation says. So we're going to be using that to solve problems. All right. So go to the next page here. Okay. And we're going to go ahead and kind of, I'm going to show you a couple examples here of how we're going to use this. All right, so assume the skier below has a mass of 50 kilograms. Okay. So let's write that down. And starts 100 meters up a 30-degree slope. Okay, 100 meters up. So they're saying that this distance here is 100 meters. Okay. Find the potential energy at the top of the hill, the kinetic energy, and the speed at the bottom. So this is 30 degrees. We do not base height on this diagonal. Okay, we base the height from the ground like that. So that would be his height. So let's go ahead and solve for the height first because this 100 is not really helping us, all right? So to get that, we would do, that's the opposite side, that's hypotenuse, so we do 100. So height is equal to 100 sine 30, which is 50. So his height is 50 meters up, okay? So if we want to know the potential at the top of the hill, meaning he starts from rest, so the potential energy at the top of the hill would be his mass times gravity times height. Okay, so 50 times 9.8 times 50. So the potential energy at the top is equal to 24,500 joules. Okay, simple enough. Now, at the bottom of the hill, he does not have any more potential energy because the height is now 0. He has all kinetic energy. So what happened was all the potential energy that he had at the top has now transferred into kinetic as he picked up speed on the way down the hill. It transferred to kinetic energy, right? So if at the top he only had potential because he wasn't moving, then the total mechanical energy at the top was 24,500. Now all that potential energy has transferred to kinetic energy at the bottom, and it should be equal to the total amount of energy he had at the top, because we can't lose or gain. So this should be 24,500 joules. Okay. Now if we know that at the bottom he has 24,500 joules of kinetic energy, then to solve for the speed, we would say that we know kinetic energy equals 1/2 mass times velocity squared. Right? If we know the kinetic energy is 24,500, we know his mass is 50, we can solve for the velocity. So 24,500 times 2 divided by 50, take the square root of the answer there, and you get that his speed at the bottom is 31.3 meters per second at the bottom. Okay, so all the mechanical energy, all the potential energy at the top transferred to kinetic energy at the bottom. Somewhere along the middle, he had both potential and kinetic, right? So halfway, he would have been split evenly. If he's higher than halfway, then he has more potential and a little bit of kinetic. If he's less than halfway, so down here, right, then he has more kinetic and a small amount of potential. But either way, they will add up to this total 24,500. Okay, so hopefully that makes sense. This picture is just showing that there's bumpy spots, right? That really doesn't change the fact that whatever the total was up here equals the total down here. Okay? So from the picture above, oops, let's scan out a little bit here. So from the picture above, sorry, find the skier's velocity when he's 3/4 of the way down the hill. So if he's 3/4 of the way down, that means that he's 1/4 the way up. So 1/4 the way up, so 1/4 of 50 is 12.5. So 1/4 the way up or 3/4 the way down would mean that his height was 12.5. So let's note that. Okay, and we want to know the velocity there. Well, if he's 3/4 the way down, then he's still moving, okay, and he still has some height. So his mechanical energy is equal to potential plus kinetic. Okay, we have both kinds of energy there. The total mechanical is what we found at the top when he had no speed and all of his energy was potential. Sorry, there was someone at the door. Okay, so we know the total mechanical is 24,500. Okay, we know the potential is going to be the mass, which is 50, times 9.8, times his height. Well, now his height is 12.5. Okay, and we know the kinetic is 1/2 times mass, velocity squared. So let's solve for this potential energy. So 50 times 9.8 times 12.5. So I'm going to rewrite this over here. We have 12,500 equals 6125 plus 1/2 of 50 is 25 v squared. I'm going to subtract 24,500 minus 6125. So I'm going to get 18,375 equals 25v squared. I'm going to divide by 25 and take the square root and get that the speed 3/4 of the way down will be 27.1 meters per second. Now it should be less than at the bottom because some of the energy is still potential. He's not all the way at the bottom, so not all the energy has transferred to kinetic. Some of it is still potential, so it should be less speed. Okay? All right, last example here. This is a spring problem, so we're going to go ahead and do this example. So you've seen one of the springs, okay? So we have a 0.25 kilogram block, so that's the mass. I'm not sure why it's capitalized there. Okay, it's placed on a vertical spring. So we have a spring like this, and we have a box placed on top of it, okay? Where the spring constant is 5,000 newtons per meter, okay? And it's pushed downward or compressed 0.1 meters, okay? So the x is the 0.1 meters. It's compressed 0.1 meters. Remember, the equation for spring potential energy is 1/2 kx squared. After the block is released, so it's pushed down and then it's released, and the box is going to shoot up, okay? So what's going to happen is now the box is going to shoot up, the spring's going to stretch back out, and this box is going to shoot up and then go to some height. It leaves the spring and continues to travel upward. What is the maximum height the block will reach? Okay, here's the trick. Right now, all the energy is stored in the spring, okay? So in this case, the mechanical energy initial is equal to the stored energy in the spring, okay? So let's solve for the initial mechanical energy here. Be 1/2 k x squared. So 0.1 times 5,000 times, 0.5 times 5,000 times 0.1 squared. So it's 25. So the mechanical energy initially is 25 joules because all the energy is stored in the spring. It's not moving and there's no height. We're gonna go ahead and ignore this height from here to here. Okay, ignore that height. So we actually don't use that. All right. Okay. Now, that mechanical energy that is stored in the spring is going to transfer to the block at its maximum height. At its maximum height, it stops moving. We know that from projectiles. So at the very, very top, the mechanical energy is equal to gravitational potential energy based on the height. So now the mechanical energy final is equal to the potential energy stored as gravity or as height. Well, we know that the mechanical energy initial and the mechanical energy final have to be equal, okay, because we can't lose or gain energy. So that means that the 25 has to equal the potential energy, the gravitational potential energy, which is mgh. Okay? So all that 25 joules of energy became gravitational potential energy. We are going to go ahead and use the mass, which is 0.25 times 9.8 times the height. So 25 divided by 0.25 divided by 9.8 gives us a height of 10.2 meters. Okay, so just overall, just so you can see this, the energy was stored in the spring. Okay, 25 joules of energy was stored in the spring. When this was released, that 25 joules of energy turned into kinetic, which shot the box upward. When it reached its maximum height, that 25 joules is stuck in the stored gravitational potential energy. Okay, and so what we did was we said the 25 joules of energy that was stored in the spring is now stored in the box at its maximum height. So we said that 25 is equal to the gravitational potential energy at the maximum height. Okay, and so that gives it a height of 10.2 meters. Okay, so write down any questions you have and we'll go ahead and answer those and go over more in class next time.